Welcome back to this session of the video on statistics and analysis. In this segment, we are going to examine how to count and also use them to apply to three examples. Right? So we're on to counting. And earlier on in the previous segment, we mentioned using factorial, permutation, and PR, and combination, and CR. So our first example is to calculate the number of ways of getting four of a kind. In a 52 card poker stack without joker, right? So just 52 cards, prim and proper. Four of a kind, what is that? That means you have example A, king. Okay, so you can also have king A, of course, but that's considered one. So if you derive various permutations of these, of course, this is like ace of spade, ace of club, ace of heart, ace of diamond, right? If you look at the suite icon, of course you can distinguish them. But if we ignore, and that's the whole point, right? We just want to look at A. In terms of winning, we just look at A, right? So if we look at the aces, then they are indistinguishable, and you can insert K into any of them, and thereby getting KAAA, AKAA, AAKA, and so on, right? So if you do that, and then amongst the KAs themselves, they can permute if you also consider the suites, the icons, and you can have SHD, CHCDS, and so on. You can have various permutations. But in terms of the hand, right? The hand, that means, did you have a winning hand? Show hand, right? Show your combination of cards. Order not considered, right now, yeah? So you can therefore sort them, let's say in standardized form from smallest to largest, all of the same type put together, so that is a representative order. So if you do that, then there is only one display, let's say, right? So here, or you can have 2222 ace, for example. So these are just examples to show what is four of a kind. Yeah, and therefore we just need to find the number of ways to obtain the first kind, the first four of the kind, and then the number of ways to get the last card, and that's all. And we don't need to permute amongst the four and with the last dangling card. We don't need to, because as we already explained, you can permute them, but they're all considered the same. So we just need to count the number of ways to get this standardized display form. And but actually I should put it as A222, right? So the standardized form is unique, all right? So all the twos, you have already got them. Whichever A, that means ace of heart, ace of diamond, whatever A you get, you put it as standardized form. So A222. Then it is unique, right? And it's considered the same as far as winning or losing is concerned. Therefore, we are going to basically say that, well, that's it, right? So we just need to consider the number of ways to get the four of a kind and then the last card. So number of ways, count, right? So W is the four of a kind. We will count the number of ways to get what we want. The W is the four of a kind, right? So at first, there are 13 suites. Remember the 52 cards in the NTUC bag, right? So there are 13 suites, 13 different numbers for us to choose. So 13C1. Once we get the number, let's say it's ace, we will have only one way. 4 choose 4. 4 choose 4 cards, right? You pick all, right? How many ways? One way. You just have one way to pick all, right? So kind of like times 4 choose 4. Basically, that's equal to 1. Okay. Then we need the last parking lot to be parked with another cart. And now the 52 carts with 4 carts already gone, we have 48 carts left. So we just take 48 carts and choose one, which basically means it's 48. That's all, right? And with a little bit of calculator or R, 13C1, 13 choose 1, that's 13. So we have 13 times 1 times 48, 624. That's it. So we are getting 624 standardized listing of 4 of a kind. So when I say standardized listing, that means like sorted in smallest number first, and then the 4 of a kind or whatever it is, you put together. So this standardized form is AAAAK, right? The standardized form for 87888, right, is going to be 78888, like this, right? So we put the smallest first, and if we get this, so we have 13 ways to choose the 888, and we pick one set of the 4 8s together. Then we have 48 cards to choose, and we pick 7. That's all, because that's the standardized form, right? And various permutations of 7 and various permutations of the 8s themselves don't matter, because they standardize to this, standard representative. So there are just 624 ways to do that. Okay, right. So let's do a quick fact check. All right. And let me switch screen. Okay, so now you can see a standard browser. And let's just ask Google's AI to find the number of ways to get 4 of a kind in standard 52 card poker without joker. Yep, okay, so the answer is 624. And the way it explains, interestingly, is basically what we have just gone through, right? So there are 13 ranks and all that stuff. 13 ways, 13 ranks, they call it. You can then choose 1 card out of the 48 remaining cards, so 64. Okay, actually, our next example is going to be number of ways to get the full house. So to do that, let's try to practice how to use our formula set again. Okay, so now we want to say calculate the number of ways to get full house. Full house is a little bit more abundant than 4 of a kind. 4 of a kind is super hard to get, right? 624. Huh? And to get full house, what is full house? Let's look at some examples. Again, let's try to express in standardized form. Right? So A, 2, 2. So that's standardized forms. And of course, that gives rise to A2, A, 2A, yeah? Or 2AA, 2A. You can permute them all you want, but they are all considered the same hand, right? In terms of winning or losing. Did you win? Did you get 4 of a kind? Did you get full house? Oh yeah, right. So whichever way you look at, it's full house. And so we represent it in a standardized form, like sorted smallest card to largest card. And within the cards themselves, if they repeat, don't care, just list them, right? So don't care about the suits. And other examples could be 2, 2, 3, 3, 3. Yeah, of course, that again can give rise to 2, 3, 3, 2, 3, 3, 2, 3, 3, 2, and so on and so forth, right? So you can just imagine. So we're just looking at the standardized form and not caring about the permutations. Okay, so calculate number of ways to get this. Well, let's look at the same logic. So the count of the wanted items is going to be, first we have 13 ways to choose the three of a kind, right? So we have 13 ways to choose three of a kind. After that, that's why we put choose 4 cards. Here we have 4 choose 3 cards, because you have 4 suites for icons. Another way to think about it is like this card. How many ways can I throw away one card out of the 4 cards, right? So there are four ways to choose which card to discard, and we keep the rest. So 4 choose 3 basically is just 4. Yeah, let's look at that. Okay, and then we need to fill up the pair right now. Yeah, so we have 12 ways to choose the number, right? And once we have chosen the number, let's say 2, and there are 4 cards that belong to this number. So now we have 4 cards, but we choose 2. Okay, so here we can quickly just do a mental calculation. 13 choose 1, that's just 13, divided by 1 factorial. Then we have 12 choose 1, so that's 12. Then we have 4 choose 2. So 4 divided by 2 factorial divided by 2 factorial. 4 factorial divided by 2 factorial, we get 4 times 3. Then divide by 2 factorial. So that's 12 divided by 2, so that's 6. So answer is 13 times 4 times 12 times 6. And we get 3744. Yeah, okay. As I say again, in case you are worrying again, oops, what about the various permutations within, right? Not to worry, because we are counting the hands, right? When you show hand, when you display, and you display 32332, people are going to take it as if it is 22333. Kind of like, let me sort the cards, right, in standard form. So whether you show your hand in a random fashion, 32332, 23323, whatever it is, right? We can always standardize it. And therefore, this is what we are looking at, not the various displaying manner, if we call this display manner, right? So this is the hand that we are looking at, the one that we are counting, the one that we are measuring, not this right hand side. Yeah. So 3744 represents the 3744 standardized form of full house that we can ever find. Okay, now again, for fact checking, right? So number of ways to get full house in a standardized 52 card poker without joker, right? So there are 3744 possible full house hands in the standardized card, right? So again, the logic as explained by this very clever Google AI machine is exactly what we have been learning, right? Exactly what humans have been learning. 13 possible ranks, they call it ranks, the numbers. We choose the cards associated with the rank, choose the rank for the pair, the number for the pair, then choose the number of cards for the number of the pair. And then we have this. Yeah. So that's how we get this done. Now, what I'm going to do is I'm going to show you the last and the final example, which is going to challenge all these things, right? Which is going to like make you think again. So all these are standardized, of course, poker winning combinations, and we need them to calculate the amount of winnings and losings. So that's why they are well studied. But let me just twist a little bit, right? So calculate, right, the number of ways to get 5 cards such that first card is ace, right? Second card is king, all right? Five cards such that first card is ace. Yeah, so find number of ways to get these hands. So just a slight twist of the description starts to make this a little bit trickier, not impossible, but a little bit trickier, right? So example, it's probably easy to, write down some examples so that we can at least see the obvious and maybe even see the less obvious. So first card is ace. Ace of spade or heart, or doesn't matter. All right. Second card is king. Third card is some other numbers, and can be king too, right? Can be ace too. And then we have ace, king, and then 3, 4, 9. Right, yeah. Or ace, king, ace, king. Possible, not impossible, right? So long as first card is ace, second card is king. So here we want to count the hands. Actually, the last part I can just remove it, right? But I just want to emphasize it's the number of hands. Remember, like when you show hand, when you show the 5 cards, ultimately. However, the formation of these 5 cards is also being described or insisted upon. That means you know yourself, right? When you receive the first card, it has to be ace. Or it can be checked by the dealer, all right, something like that. So the first card has to be ace. The way you form the 5 cards, the ultimate 5 cards that you win or you lose, has to be such that the first card is ace, second card is king. So find the number of such hands rather than display format, because you see the mere mention of first card, second card, kind of tells you as if there's an order right now, that as if the order matters. Remember, we said order matters a lot. You better check whether the question wants order or not. So the order does matter in terms of forming the 5 cards. However, the question really wants the final combination of 5 cards, just like the full house, just like the 4 of kind. So it doesn't matter how the cards were permuted internally, perhaps at the 3rd card, 4th card, or the 5th card before the player shows the 5 cards. Okay, so that's a very important understanding. So let's start counting. So now what we want is we need to have ace, right? So that part is fixed. 1 choose 1, but don't have to write that. So instead of 13 choose 1, we have 1 choose 1. We choose ace. It's stated, no other choice. So, but then out of the 4 cards, we can choose 1. So we can choose 4. Out of 4 cards, we choose 1 ace. That's equal to 4. For the second card, it has to be king, right? So there's no overlap. If we choose ace in the first card, the second card still has 4 kings in the plastic bag, right, of cards. So we still have 4C1, and that's for the king. Okay, so far so good, and things are looking the same. First, second, and then we have the third card. Okay, the third card, and the third card. Now here it gets a little bit tricky. Should we say, okay, 52 cards, right? So we picked away 2 cards, so we have 50 cards left in the bag. Should we say 50 choose 3, or should we do 49, sorry, 50 choose 1 times 49 choose 1 times 48 choose 1. The answers are different. So which way should we do? Give you 3 seconds to think. 3, 2, 1. Yeah. Okay. So if we do 50 choose 3, we are saying that the last 3 cards, we don't care about the order, right? And indeed, we don't care. However, what we really don't care about is actually the final hand of 5 cards, including the first 2 cards that have been fixed. See that? Yeah. So that's why it is important to follow through the order first, then jumble them up, and then remove the permutations. Here's how, right? So following the same ordering, okay, we can kind of reinterpret the question as first card has to be ace, fine. Second card has to be king, fine. Third card has to be anything or anything. Fourth card has to be any of the remainder. Fifth card has to be any of the remainder, right? We can say that, yeah? So we can do that. And we say, well, there are 50 cards at this point in time. We choose one. 49 cards after that. 48 cards after that. So if you do 50 choose 3, you are saying these 3 cards alone, the permutation don't matter. But what about these 2? So you get into some sort of a difficulty there. So by doing this is also not fully right, but it's more in order of what is described in this question. The order matters, right? First card A, second card king, third card, whatever is in the remaining, then 49, whatever is yet in the remaining, and then yet in the remaining, right? So by doing this, we overcounted, because we are talking about 2, 3, 4. Let's say the card is 2, 3, 4. And if we got 4, 3, 2, 3, 4, 2, 3, 2, 4, they are all supposed to be considered the same. So we need to do something here first, right? So what we need to do is that so far, these whole 5 terms have counted the correct permutation for the 5 card combinations that satisfies the first card is A, second card is king requirement. What we need to do is to remove the permutation within these 5 cards. Yeah, and if you recall, to introduce permutation into 5 cards in order to get to introduce permutations into a combination in order to get the permutation, we multiply by the cards number factorial, right? So here's what we need to do. There are 5 cards. So what we do is we just multiply by 5 factorial. In this case, this is the permutation. So we kind of divide it by the 5 factorial. Okay. So this has overcounted 2, 3, 4, 2, 3, 2, 4, and so on. And also 2 ace, king, 3, 4. 2 king, ace, 4, 3, and various permutations. Right or not, yeah? So we need to get rid of those because they're supposed to be 1. They're supposed to be 1. So like I said, it's like AK349, right? So this 50 choose 1, 49 choose 1, 48 choose 1 also includes AK943, AK493 of the same exact icon or suit, which is overcounting, right? So what we then need to get rid of is not just the overcounting of these 3, but also including these 2. And that's why it's 5 card permutation. 5 card permutation, that is of the size of 5 factorial. So we divide that, we get rid of the permutations within our little group of 5 cards hand here. Okay, so if we did everything correctly, we should not be getting decimal places, because there's a bit of fear that are we doing the right math? Are we going to get decimal places? So 4 times 4 times 50 times 49 times 48 divided by 5 factorial. That's supposed to be 120. Okay, so that is 15680. 5 factorial, right? 5 factorial. Yeah, 120. So 15680. Okay, so all these have been counting, and the same question can be rephrased in a quiz or test by calculating the probabilities of getting four of a kind, full house. The 5-card combination such that first card is A, second card is King. Right? So counting and finding probability is very closely related. Why? Because counting the universal set, right? That is, I want to have a 5-card combination. Don't care about the order within the 5-card combination, correct? Just draw 5 cards. Do I get a 4 of a kind, right? So simply just 52, choose 5 cards. Yeah. So if we do that, then fortunately I have a little device here that actually works. I get 2, 5, 9, 8, 9, 6, 0. And our probability is just one division away. So for this, the probability is C of W over C of U, and that is just 624 over 2598960. Okay, so 624 over 2598. So wow, very, very small. Okay, so the kind of standardize it is 0.00024 and then 0096, but that's enough. Then the probability of getting the 3 of a kind is again C of W. You see, whenever you can count, right? It's a lot easier. And with the use of factorial combination permutation, counting these like number of ways, number of combinations gets so easy. So long as, of course, you do it the right way. 8960. Yeah. Okay, so 3744 divided by 2598960. You get, also small, but of course noticeably larger, 0.00144. Now, the easiest way is to look at the numerator, right? Because the denominator doesn't change. So over here, and just to be symmetrical about things, in this last case, we can say that, this kind of combination, which is like when you draw the cards, right? Initially draw 2 cards. What's the chance that I end up getting a good card? Good card meaning ace and king for the first 2 cards, right? And it has to be like that. It cannot be king and ace. So we have yet to include that as well. So ace and king. So ace and king, like that. The number of ways, 1, 5, 6, 8, 0. So probability of getting this is C of W over C of U, and that is 15680 over 2598960. 15680 over 2598960. And it is a smallish number, 0.00603. Okay, so that is an illustration, right, on how you can perform all the counting and all the probability calculations. Okay, see you in the next video. Thank you.